Okay, so here I am, and I hope that from now on everything will be okay. Okay, excuse me again, all audience, for my late coming, and I promise to try my best. And I like to present a new technology, a novel technology, but it's novel, but already with application on several thousands hectares. So it's novel, but already working. Let me explain you'll see that the title that we put here, Could Forever Change Agriculture. This was given to us by Bloomberg Business Week in an article that was published on last September. They review our technology, and they say that, well, you know, everything is maybe, but if it works, this piece of dripper that we present that is totally different than common drippers, it can change agriculture. Let me describe first the mission, but then how we came to this situation. And the mission is to lead effort in solving the global water shortage by providing the ultimate alternative to flood irrigation, enabling farmers precise, cost-efficient, and sustainable solution. As you can see here, we deal not only with water, but we deal with water, food, and gases and emissions, or as we call it today, all the things that affect the global change, climate change. I was the water commissioner of Israel. In my time, Israel changed from ever being subject to so sensitive to amount of precipitation to a state that is insensitive to the amount of precipitation by efficient and by desalination. Efficient means recycling, and desalination gives extra water to the people. Yet, when being involved in many international organizations, it became very clear that water is the #1 natural resource that the world is depending on, and that it is in shortage. And then when you zoom in, you realize that 70% of all water that human is using is used for agriculture, for irrigation. When you zoom again inside, you realize that the efficiency of this irrigation is only 25 to 30%. So I say to myself, wow. Then it's very clear that if we need to deal with water problems in the world, we need to do it through the irrigation. If 70% of all water is used for irrigation, and this irrigation is in the efficiency of only 25%, that means that this is where we need to do it. And then when you zoom in again, you realize that why it's only 25 to 30%, and this is because the world is still using to produce food a technology that was invented or developed about 5,000 years ago by the Sumerians, which we call flood irrigation. It's crazy. This is the main technology that we use today to produce our food. It's 5,000 years old. And you say, well, this is true in some remote places in the world. No. This is in China, this is in California, this is in Texas, this is in Spain, this is in Australia, this is in Italy, anywhere. This is the main irrigation method. And it's not efficient. It can't be efficient. If you let the water go into the field in one place, wait until the water comes to the end of the field. It's very clear that the point where you let the water in infiltrate much more water than the last the end of the field. Can't be differently. So the distribution of the water in the field is not uniform, and we lose water. So what happened with drip irrigation? Drip irrigation is a technology that is also old already. It's 60 years old. It's only 3.5% of the irrigated land. That's all. So it's not a solution. Knowing that, I started to think, and the truth, today the word hybrid is very common. So we have hybrid cars and hybrid so many things. What you see is a hybrid that takes the good things from flood irrigation, that is free energy, and infrastructure is very cheap, and the precision of the drip irrigation. What we do drip irrigation by gravity. What we had to come over, how to do it in a very low head or pressure or energy, practically to use no energy, and how we solve, if you don't use any energy, how we solve the problem of the getting the dripper plugging. So how is the normal flood irrigation works? Normally you have the canal that brings water to the field from the river, and then you have siphons or other method that takes water into the field. This is the common method. Now, in this common method, it's need that the canal is a little bit higher than the field, because if not, water will not come to the end. What we have in our drip system, we have the same canal, the same field, but we take the water from the canal into a simple drum with a floating valve, and from there we run with drip irrigation that gives precise amount of water to every plant. By doing that, we reduce the water up to 60%. We reduce the fertilizers up to 60%. We reduce the CO2 or methane by up to 80%, and we maximize the yield. So we get all this with increasing yield. How this miracle is done? Okay, this is to show again the advantages, and you can see them. But let me, how this is done. This is done simply by changing the drippers. All drippers in the world are what you see on the right side. Water goes into the dripper, then they runs through a kind of a zigzag where the water pressure is reduced to get the exact amount that we want outside. The problem is that all water flows in the same path. And if this path is getting plugged because of particles or anything, the dripper is blocked. Our dripper here, this dripper, works differently. You see what we have in here is a simple cylinder that smoothly takes the water to the end, but of course, this will not create a uniform water distribution along the lateral. So inside, we insert this rod that you see here. We insert it here, and the water flows in the ring between this rod and the cylinder. The size of the difference, the gap between the size of the ring sets the dripper discharge, but the point and this fits, this method fits very well to know, we don't need any pressure to force the water through, but it still set the volume, and we cannot plug it very simply because no single particle can block the ring. It only blocks a portion of the ring. If it blocks a portion of the ring, the water easily bypass it. We call it a multi-dimensional water flow. So unlike the common dripper that we have one, it can be in a different direction, but all the water flow in the same path. In a ring, the water can flow directly around the ring in each side, if you have any blockage, they simply bypass it and then they let it go. So it works. Let me show you the difference in why we have the difference. This is two fields in California near Sacramento. The left one is with a common pressurized drip. The right one is done with N-Drip. So you see that for the left one, you need first you need a generator, then you need a pump, then you need a battery of filters. You need capex with about $2,000 per acre. In N-Drip, we have this small drum or container or tank that takes the water from the water canal. The water canal is here. We both take the water the same. Send the water to the dripper, and for the plants, there's no difference. They see the dripper. And this costs $350. Because it costs $350, it is affordable. And farmer can buy it. The ROI, the return on the investment, is within the first year. It takes 9 years in the other one. This is why people don't buy it. Farmers don't buy it. They don't buy it. They use the cheapest method, flood the wastewater. It's like water has no value. N-Drip works well. You can see here several, again, the same idea. This is what you see here is the end of the canal. Why I don't see it well? You see here the canal that we take the water from, the small drum, and field of sugarcane, field of corn, field of cotton, field of alfalfa, field of everything. We brought the dripper to the field crops. That's all kinds of method we use. Now, in order to make the system real precise, we combine the system with sensoring measurements and algorithm that can tell everybody that use this N-Drip exactly what the status of any parameter in his crop. Let me say it this way. First, in order to get good data in order to use good algorithm, you need good data. You know, before the big data and before the AI, before the artificial intelligence, we used models. And in the models, we used to say that garbage in, garbage out. If you don't have good data, you don't have good output. Today, with the big data, that we use much more data, and we use them then we use them also for artificial intelligence, we need even better data. Now, it's very difficult to get good data in the field. Why it's difficult? Because it's very difficult to measure, it's very difficult to calibrate. When I come to a farmer and tell him, look at my new system, he say, okay, maybe, depends of course how much it costs, but first, you come with me to my museum and I'll show you all the sensors I bought in the last 20 years and I never used them. It doesn't work. So we build something that is work and it works with this system. And the idea is that if you look in this figure, it tells you the noise, the value of any parameter. Let's say it could be soil water, the soil moisture, and this is a sampling volume. And you see that if the volume that we sample is very small, the noise is very high. I can explain it, but you could understand. You could hit a warm pore. You could hit a small stone. All you have is a sensor of 1 square inch or something like that. It's too small. When we increase the sampling volume, we decrease the noise and get a much less variability. So what we did here, we took here, you see here the sensor, And the sensor is built around a very specifically designed with the properties of a ceramic textile that sample very efficiently the entire root zone. When it samples the entire root zone, we know that we are here. The result of the size and the types are the results of two PhD dissertations, and this is the output of this. Now that we have very good data, we can combine it with the models that simulate practically everything that happens in the field. It takes the water flow, the salt transport, nitrogen fate, root growth, canopy growth, fruiting, or any phenomena that happen in the plant. These model, the model that we use now in this group was developed by many groups around the world. I can say in California, in Holland, in Wageningen, in Stockholm, in the KTH, in the Hebrew University, in Logan, Utah, and each group combines something. And we got a model that is very good. It's very good, but it is used by PhD students. It is used in a model in climate change in many places, but not in agriculture. Why not? Because you need too much data. And the farmer or the expert even, they cannot get this kind of data. Now, because we have this very exact sensor, we can calibrate the model to work with us. So we end up with having a very precise irrigation method with very precise information that comes from the field. Now we can optimize the growth. We can optimize it to yield. We can optimize it for the environment. We can optimize it for carbon fixation. We can optimize it for time of harvest with an efficient system. And efficient system that fits the 21st century, and it's cheap. So you can see the sensor and the way that we work with it. We have the sensor, we have the models and the big data that, and this is the learning system that learn all the time. Just to show you some results, this is, for example, a work that we did we cooperate now with PepsiCo, that they, on this program, they understood that they need to save water and to be more sustainable. So we work together. And this is a field in Nebraska. And you can see that, American, they measure the amount of water with acre foot. Acre foot, it's about 1,200 cubic meters for anybody, but it doesn't matter. Look at the numbers. So irrigation of this field of soybeans, N-Drip irrigate 1.53 acre foots, flood 3, CO2 emission 54 for the N-Drip system, 350 for the common flood. Yield higher here than there. So it's a solution that can work. This is the same result that we got in, for example, in India for, again, this is for potatoes, and you can see that the green is the amount of water we use to get the yield. This is in Punjab, this is in Rajasthan. Look, this is flood, this is N-Drip, flood, N-Drip, and so on. It's the average water reduction is 50%, average yield increase is 13%. So what's the question? This is in California. We use it on alfalfa to grow, a lot of water is wasted when we grow silage for the meat or milk industries. Okay, let's not discuss how much it's necessary now, but we can save 50% of the water just by changing the system from the common flood to this method. Well, pictures are nice, I think. This is the data from for alfalfa. We use at the same time that we use when we use the sensor, of course, we use the satellites and to compare the data. And now we learn how to to use the very exact sensors, yes, that we have to make the satellites data normalized also to our sensor, so we can take the larger fields and so on. I believe that I'm almost on time, no? Thank you very much.